Hi, Algebra 2 honor students. This is going to be Unit 4, Day 2 on solving systems of equations. So if you want to take out some paper to take some notes by hand, you don't necessarily need graph paper for today. I just like the way the grid lines kind of help me organize my work for certain steps in this process. You probably will need graph paper later in the unit for things we'll physically be graphing. But for today, if you just have line paper, that should be fine. So taking a look at this first example, on the day 1 notes in page 24 in the packet, there were two methods that were shown about how to solve systems of equations. There was that substitution technique and then also elimination. And if you look at the way these terms are kind of lined up in this first initial example here, when you have the x-ish terms lined up and the y terms and the constants, this is nicely set up to use elimination. However, I think a lot of us are looking at this and saying, whoa, I've never solved anything where we don't have anything that looks linear in nature. So we have to be a little bit cautious then about how are we going to wind up solving this. And I think the best approach is to actually use some dummy variables. So if we, off to the side, let's let a equal 1 over x. And on the other hand, just let b equal 1 over y. We can transform this into a system that we feel a lot more confident solving. So if 1 over x is a, this is going to turn into the top equation saying a minus 1 over y is b. So therefore, a minus b equals 3. And then for the bottom equation, if we have 2 over x, that's going to turn into, that's the same thing as 2 times 1 over x, right? So that would be 2a plus 3b is equal to negative 4. And now this is a system that I'm hoping you feel pretty confident to solve. You can choose whichever variable you'd like to eliminate, whether you want to eliminate a or b, it's kind of up to you. Let's say I eliminate a by multiplying the top equation by negative 2. So just make sure you do that on both sides of the equation. So that's going to turn into negative 2a plus 2b is equal to, on the other side, negative 6. So when I add going down vertically here, like I said, our a's are going to cancel out, which is what our goal is. And 3 plus 2 is going to be 5b is equal to, on the other side, negative 10. So therefore, b is equal to negative 2. All right, perfect. We know that once we solve for one variable in a system, we can then easily plug it back in to find the value of the other variable. I would say just be a little bit careful if you plug it into the top equation there. When you plug in negative 2 for b, you would write it as a minus negative 2 equals 3, which is going to become a plus 2 then, right? So it's probably easy to kind of lose that double negative when you plug in negative 2 there, but therefore a equals 1. Now the last step in this process is, although, yeah, elimination, great, we remember how to do that, we have to remember that these are dummy variables. These we just let substitute in for the quantities 1 over x and 1 over y. So I guess that begs the question then, if a equals 1 over x, you can go back and re-sub in 1 over x at this point, and then you have to get x alone, don't you? But pretty simply, if you were to get x alone in this, wouldn't x just equal 1 over a? Right? Multiply both sides by x, divide the a back over, and similarly, y is equal to 1 over b. Okay? So if you wind up just taking the reciprocal of these values, you're going to get your values for x and y. So if a is equal to 1, then that means that x is equal to 1 over 1, which is still 1. So therefore, x equals 1. Hopefully remember 3 dots in a triangle means therefore. And if b equals negative 2, then y would equal 1 over negative 2, which is negative 1/2. So the solution to the system of equations would wind up being 1 comma negative 1/2. And typically you'll see solutions written as a coordinate point, something of that form. You don't have to write it that way. If you get x and y and you kind of box them in, that's kind of good. But remember, what does the solution to that system graphically represent? This is the point of intersection of these two equations right here. Okay. So probably a little bit of a different look to get started in this example here, but with some quick substitution, some dummy variables there, and then using the elimination technique, you can easily find a and b, resub in x and y, and kind of go from there. I think we'll see that technique come up in future examples, so hopefully we'll think to do it. But what we're going to move on to talk about today is, I think we're pretty good at 2x2 systems. Let's talk about 3x3 systems. So what is a 3x3 system? A 3x3 system is when you have 3 equations with 3 unknown variables. So not only do we have x, not only do we have y, but in most cases we're going to have z as a third variable. And when you have 3 variables, you need at least 3 equations in order to solve the system. So if we had 3 variables and 2 unknowns, that would be much more challenging for us to do. So my first step is to choose a pair of equations, that's what I mean by a pair, and eliminate a variable. So although I would probably call that var and not var at the end, I like the way it rhymes if you say choose a pair, eliminate a var. So choose a pair of equations, eliminate a variable there. So that's going to be something we're pretty confident with. That's what we just did up in the warm-up question at the start of the notes here. We eliminated the variable a up there. So I'll look at my 3 pairs or my 3 sets of equations and hopefully be able to easily pick out a variable I want to eliminate. Then step 2 is choose a different pair from what you chose in step 1, but you have to eliminate the same variable from that equation. So if you chose a pair in step 1 and eliminate y, when you choose a different pair of equations for step 2, you have to eliminate y again. Because what is that doing? It's creating 2 new equations. But now you only have 2 variables within those equations. And those 2 variables will be matched up because you're eliminating the same variable again. So what you've now reduced this to is you had a 3x3 system, but now we have a 2x2 system. And you're going to solve that using elimination, just like we did up here, and then do what I call back substitute. So once you find the value of the first variable, plug it in to find the second in your 2x2 system. Then take both of those answers, go back to the original 3x3 system, and find one of the missing variables. And I hope this is kind of making some sense as you're writing these steps in your notes. But if not, certainly we're going to get some practice with that now, and hopefully we'll put these steps into good practice. You may find yourself pausing along the way because I think, our examples mostly just written out today. So if you need to, hit pause and copy this down. But in the first example, we're going to solve x minus y plus 2z equals 3. 2x plus y minus z equals 3. And 3x plus 2y minus 4z is equal to -1. One thing I'll really encourage you to do as you're copying this down is make sure that you're copying it down correctly. Because even if you miss one little minus sign or forget one coefficient along the way, that's going to, of course, affect the answers that you get in the end. And sometimes students come up to me and they show me their work, and I'm like, hey, great job, except I know that you got this wrong because you copied the first equation incorrectly. So that's kind of heartbreaking to tell a student. They may have solved their system correctly, but the actual system that was given to them, if you copy something wrong, yeah, you're definitely going to get different answers. So taking a look at what we have in our variables here. We have the x is nicely lined up, the y is nicely lined up, and the z is nicely lined up. And if you look at each of those sets of variables there, I want you to think about which looks like a nice pair of equations to choose first, such that we can easily eliminate a variable. And there's really no right or wrong. I mean, I think there is one that's easiest to choose to get started. But in the end, if you wind up choosing a different pair, we're still going to get to the same place. I'm going to choose the first and second pair because what I notice is in the middle, we have -y and +y. So if you add those first 2 equations together, the y's automatically get eliminated. So when you eliminate y here, we're going to get x plus 2x, which is 3x, 2z plus -z, which is a +1z, and I'll add the values on the other side. 3 plus 3 is 6. So that was pretty easy. First step, I chose these first 2 equations, added them up, and was able to eliminate y. So in step 2, we have to choose now a different pair of equations, either the second and third or the first and third, doesn't matter. And we want to eliminate y again. I'm going to choose the first and third equations. It really doesn't matter, but if I multiply this top equation here all by 2, notice how a -2y is going to cancel out with a +2y. So that's what we have to think about. If I take this whole equation up here and multiply everything by 2, we would get 2x minus 2y plus 4z is equal to 6. Just recopy the bottom equation, 3x plus 2y minus 4z is equal to negative 1. All right, so upon doing this here, okay, if I wind up adding those equations together, what winds up happening is the 2y and negative 2y cancel out. So we're going to get that 5x. And then what's interesting here is that the 4z and negative 4z also cancel out. That wasn't really expected to happen. But when it does, it's kind of nice, because then what do I get on the other side? 5x is equal to 6 plus negative 1, which is 5. And all of a sudden, we now know that x equals 1. So this isn't typically what would happen in this system, but usually you would still have a z in this equation. And then we would come up here and write that equation with x and z in it and solve this little mini 2x2 system. But we don't have a 2x2 system anymore. We already know that x is equal to 1. So if x equals 1, come over here and plug it in for x in this equation and solve for z. So if 3 plus z is equal to 6, that must mean that z is 3. By the way, notice how I put my line through my z every time? I really think that's a good strategy, just because z's and 2's can look so similar to one another, especially depending on how you write them. So good strategy there. All right, if z equals 3, how do I find the value of y? Got to go back to any of the original equations. Doesn't really matter. I kind of like the middle just because y is positive and by itself already. So if we go back to 2x plus y minus z equals 3. In this instance, we're going to plug in 1 for x. We're going to plug in 3 for z. And we'll solve for y. So if I combine like terms, 2 minus 3 is a total of minus 1 on that side. So if y minus 1 equals 3, we would get that y is equal to 4. And just kind of at the end of the process here, when I write my solution, remember when we wrote our answer earlier as an xy coordinate pair? You can actually write this as an xyz pair now. So xyz, what we're looking at here is 1, 4, and 3 is a nice way to represent that solution, just in the order x, y, z. And if you're trying to think about, well, what does this look like? This is taking things to a third dimension. You know, if you were to graph things with an x-axis and a y-axis, and also a z-axis, we're getting to thinking about three-dimensional planes and things intersecting with those planes and where that's occurring. And it's tough to visualize graphically, but maybe in upper level math courses, like even in pre-calc honors, you start to see a little bit more of talking about things like this in a three-dimensional sense. For now, we'll just work on the algebra to get to the solution. Okay, perfect. We've got number 1 done. Here's another example for us to look at. We've got 4x minus y plus 3z is equal to 1. X plus y minus z equals 2. And then 6x plus y plus z is equal to 4. So to get started here, again, you want to kind of look at your x's, look at your y's, look at your z's, what might be easiest to eliminate. And when I do this, I'm looking at the top pair again, and I'm like, hey, I can eliminate y pretty easily again if I just add those two together, can't I? So when I do that, we're going to get a total of 5x. And then over here, we're going to get plus 2z is equal to 1 plus 2, which is 3. So then, of course, we want to choose another pair and go through the same process. You know, it's up to you what your other pair is. If you choose, let's say, the second and third equations, we have to eliminate y again. Maybe I'll go through and I'll negate everything in equation 2, right, the second row, so that this becomes a negative y. So if I do that, I get x, then a minus y, I'm sorry, negative x, right? I'm multiplying everything here by -1. So negative x minus y, then it's plus z is equal to, over on this side, -2. Combine that with 6x plus y plus z is equal to 4. Okay, add those up. Definitely y gets eliminated again. And we get 5x plus 2z is equal to -2 plus 4, which is going to wind up equaling 2 in this case. So now it's a little bit of a different scenario. Last time we already had x alone after doing that second set of elimination. But notice here how we still have another equation with x and z in it. So all you're going to do is you're going to carry that equation up here. And now you're going to solve this system. And in order to solve this system, what you want to do is you want to choose a variable to eliminate. Either eliminate x or eliminate z. Let's say I want to eliminate the x. So we have 5x and 5x here. I like multiplying by -1, although essentially what you could do is instead of multiplying an equation by -1, let me just show you what that would look like. You could just subtract the equations and subtract going down the line. Students do tend to make more mistakes with that, so I always like thinking of it in terms of addition. But when I add up here, 5x and -5x go away, so that's what we thought would happen. And then, this is weird, 2z and -2z go away. So what do we have on the left side? 5x, -5x, 2z, -2z. There's nothing left over there. It's 0. And what does 0 equal? Of course, in mathematics, 0 is equal to -1. What? What does that mean? I don't know. All right. Well, here's exactly what it means. Hopefully this stood out to you, but there's actually no solution to the system. So if we think about a solution as being kind of an intersection place, there's no intersection among these three original equations. That's what we're finding. And if you look at this 2x2 system we reduced it to, there's no way if x, depending on what x and z are, for 5x plus 2z to equal 3, and also for 5x plus 2z to equal 2. Right? No matter what I plug in for x and z there, we can never get something that would make both of those equations true, which makes sense to me as to why we get no solution in the end. So if you didn't notice that when we were kind of going through the elimination process, that's fine. But what I want you to think about is, okay, well, if you get something that looks like this and you do the elimination process, if you ever get this goofy thing that says 0 equals really any number on this side, when 0 equals -1, there's definitely no solution to that system. Okay, we're going to finish up today's lesson with one more example. We've got this one for you. It's pretty similar to the warm-up questions, so I'll give you a second to copy it down there. Hopefully you're thinking what I'm thinking we should do to kind of simplify the process here. Whenever you see these fractions, I'm definitely thinking we should use some dummy variables to simplify this and reduce it to something that's easier for us to solve. So we get a equals 1 over x. I'm going to let b equal 1 over y. And then c equal 1 over z. I think those are the easiest things to choose. I've had students suggest other things in the past. Like, for example, could I call b 2 over y? Because we see 2 over y here and here. And the answer is yes. You just have to think carefully then about what 4 over y becomes. But just to make my life pretty easy, I'm going to make 1 over x, 1 over y, and 1 over z equal to a, b, and c. And when I do that, then I can now go back to the system and change this into 3a minus 4b minus 2c is equal to -1. Middle row would say a plus 2b plus c is equal to 3. Bottom row, 2a plus 2b plus 2c is equal to 5. All right, so now we want to start picking some pairs of equations and doing some elimination here. Let's go ahead and take a look at my variables, a's, b's, and c's. Is it easier to eliminate one as opposed to the other? All right, I think what I'm looking at kind of right off the bat is if I look at the first and third equation, notice how we have a -2c and a +2c. So all I have to do is add those together and the c's are eliminated. So that might not be a bad pair to start with. What would happen with the other corresponding terms? 3a plus 2a is 5a. Negative 4b plus 2b is a minus 2b. And then here we saw the c's would cancel. Negative 1 plus 5 is going to wind up being 4. Okay, so then we would just want to choose another pair and also eliminate the variable c. So maybe what I'll do is I'll choose the second and third equations. Okay, if this one has 2c and this one just has c in it, we have to multiply the second equation by negative 2, such that we can then eliminate the variable c when I add these two together. So that would be negative 2a minus 4b minus 2c is equal to negative 6 on the other side. Okay, make sure you carefully do this. So then when I go ahead and add those together, 2a and negative 2a cancel out. So that was kind of curious because that wasn't even what I was trying to eliminate. I was trying to eliminate c over here. But the a's cancel out as well. 2b minus 4b is a total of negative 2b. And then 5 plus negative 6 winds up being negative 1. So in this case, you get b equals 1/2. So yeah, that was kind of similar to the first example that we did, that we were trying to eliminate c, but we kind of got lucky in the process and wound up eliminating a as well. So if b equals 1/2, I can now sub that directly into this equation that we determined over here. 5a minus 2 times 1/2 is equal to 4. Well, half of 2 is 1. Add that 1 over. If 5a equals 5, then a must be 1. Okay, and then finally, we got to go back to any of those original equations, plug them in to solve for c. I kind of like the middle row. Those seem like the easiest coefficients. So if we go to a plus 2b plus c equals 3, then we would get 1 plus 2 times 1/2 plus c equals 3. And this looks like it's going to be a total of 1 plus 1, right? Half of 2 is 1. So 2 plus c is 3, and therefore c is 1. And just got to be a little cautious here as we get really excited. We got our values for a, b, and c. However, we know that those were actually equal to these, the original variables in the question here. So if a is 1, then x would be 1 over 1, which is just 1. If b is 1/2, then y is going to be 1 divided by 1/2, which is now 2. You're essentially just finding the reciprocals of all these, and therefore z would also be 1. So the solution to the original system is 1, 2, 1. Okay. So next time I see you, we're just going to do a lot more practice with solving 3x3 systems, and maybe even introduce some word problem situations where we have to come up with the equations based on a given scenario and then solve the system from there. All right, that's it for this lesson. We'll see you next time.